December 7, 1941. Pearl Harbor burns. America declares war on Japan the next day, and within 72 hours, the United States military faces a crisis that threatens to cripple the entire war effort before it even begins. Japan controls 90% of the world's natural rubber supply. Every tire on every Jeep, truck, tank, and aircraft requires rubber. Every gasket, every seal, every hose in 12 million military vehicles depends on it. The Army calculates they need 600,000 tons of rubber per year just to maintain operations. America's strategic reserve contains enough rubber for less than 1 year of war. The solution seems impossible. Create rubber from thin air. Or more precisely, create it from petroleum and chemicals in a laboratory. Then scale it to industrial production before the reserves run out. This is the story of how American chemical engineers, working in factories across the nation, solved what experts called the most critical materials crisis of World War II. January 1942. The Japanese advance moves faster than anyone predicted. Singapore falls on February 15th. The Dutch East Indies surrender on March 9th. Within 90 days of Pearl Harbor, Japan controls Malaya, the Dutch East Indies, and French Indochina. These territories produce 92% of global natural rubber from rubber tree plantations that took decades to establish. The numbers are stark. America enters the war with 630,000 tons of crude rubber in the strategic stockpile. Military planners calculate consumption at 840,000 tons per year for full war production. At current usage rates, the stockpile will be exhausted by late 1943. The War Production Board issues its first assessment on January 20, 1942. The rubber situation is the most critical raw material problem facing the nation. Each B-17 bomber requires 1/2 ton of rubber. A battleship needs 75 tons. A single Jeep requires 32 pounds just for tires, plus another 18 pounds for hoses, gaskets, and seals. The military plans to build 12 million vehicles. The mathematics are brutal. 12 million vehicles times 50 pounds of rubber per vehicle equals 600 million pounds minimum. And that's before calculating replacement tires, which wear out every 5,000 miles under military conditions. President Roosevelt creates the Rubber Reserve Company on June 28, 1940, anticipating the crisis. The agency stockpiles every pound of natural rubber it can purchase. But there's not enough. By January 1942, the price of crude rubber jumps from 18 cents per pound to 43 cents. The market panics. Bernard Baruch, chairman of the War Production Board's Rubber Committee, delivers his report to Congress in September 1942. We face both a military and civilian catastrophe. Of all critical and strategic materials, rubber is the one which presents the greatest threat to the safety of our nation and the success of the Allied cause. Civilian tire production stops entirely in January 1942. The government imposes a nationwide 35-mile-per-hour speed limit to conserve rubber. Scrap rubber drives collect 700,000 tons from basements and garages across America. It's not nearly enough. The solution has to come from chemistry. Rubber is a polymer. Long chains of molecules called isoprene units that link together. Natural rubber from rubber trees contains these chains in a structure that makes the material elastic and durable. The challenge is recreating that molecular structure artificially. Germany attempted synthetic rubber production in World War I and continued development through the 1930s. By 1941, German factories produced 25,000 tons per year of Buna rubber, named for butadiene and sodium, its key components. German Buna works, but it's inferior to natural rubber in almost every application. Tires made from pure Buna wear out 3 times faster than natural rubber tires. American chemical companies studied synthetic rubber since the 1920s but never prioritized it. Why invest in expensive synthetic production when cheap natural rubber flows from Southeast Asian plantations? Now those plantations belong to Japan. 4 American companies hold the key knowledge. Standard Oil of New Jersey, which has a technology sharing agreement with IG Farben in Germany. DuPont, with its polymer chemistry expertise, Goodyear, which experimented with synthetic rubber compounds, and U.S. Rubber Company, which developed a small pilot program. The government needs to scale from laboratory experiments to industrial production in less than 2 years. The first question: which synthetic rubber formula? German Bühner uses butadiene and styrene. It produces a rubber that works for some applications but fails under extreme temperatures. It gets brittle in cold weather and soft in heat. American military vehicles operate from Alaska to North Africa. The temperature range runs from -60 degrees Fahrenheit to +130 degrees. Standard Oil scientists, working with IG Farben's research, develop a modified formula adding styrene at a different ratio. They call it Bühnes, and it shows promise. DuPont develops neoprene, a synthetic that resists oil and chemicals better than natural rubber. It's perfect for gaskets and hoses, but too expensive for tires. The second question: where do the raw materials come from? Synthetic rubber requires enormous quantities of petroleum derivatives, particularly butadiene. America produces 30 million barrels of petroleum per year in 1941, but refining it into the specific chemicals needed for synthetic rubber requires building entirely new facilities. The War Production Board makes the decision in January 1942. Build everything simultaneously. Design the plants, develop the chemistry, train the workers, and scale to full production all at once. There's no time for sequential development. The target: 700,000 tons of synthetic rubber per year by the end of 1943. The Rubber Reserve Company awards the first contracts in February 1942. 51 synthetic rubber plants will be built across America. 15 plants will produce butadiene from petroleum. 8 plants will produce styrene. 28 plants will polymerize these chemicals into synthetic rubber. The government invests $700 million, the largest industrial project in American history, aside from the Manhattan Project. For comparison, the entire American automobile industry in 1941 was valued at $600 million. The engineering challenge is staggering. Each synthetic rubber plant requires specialized equipment that doesn't exist yet. The polymerization reactors are 40 feet tall and must maintain precise temperature control to ±2 degrees Fahrenheit. The chemical reactions are violent. One mistake and the entire batch is ruined, or worse, the reactor explodes. The first plant breaks ground in Akron, Ohio. In March 1942, the Goodyear facility will produce 30,000 tons per year. Construction crews work 3 shifts, 24 hours a day. The plant must be operational by January 1943. Chemical engineers face immediate problems. The German Bühnes formula uses emulsion polymerization, where the chemicals are suspended in water with soap. The process is slow, taking 14 hours per batch, and the resulting rubber varies in quality. Some batches are excellent, others are useless. Dr. Waldo Semeny at BF Goodrich leads a team searching for improvements. They experiment with different catalysts, different temperatures, different reaction times. The goal is consistent quality and faster production. Every hour saved per batch means thousands of additional tons per year. Meanwhile, petroleum refineries rush to produce butadiene. Standard Oil builds a massive butadiene plant at Baton Rouge, Louisiana. The facility processes 100,000 barrels of petroleum per day, extracting the specific hydrocarbon fractions needed for rubber synthesis. The plant costs $45 million and takes 9 months to build. Styrene production faces similar challenges. Dow Chemical constructs a styrene plant at Freeport, Texas. The plant starts with ethylbenzene, puts it through a series of chemical reactions at high temperature and pressure, and produces styrene monomer. The entire process, from crude oil to finished styrene, takes 72 hours and requires absolute purity. Even small contamination ruins the final rubber. The government creates the Synthetic Rubber Program Office to coordinate everything. Jesse Jones, Secretary of Commerce, oversees the operation. The office assigns priorities, allocates materials, and resolves disputes. When a plant needs steel for reactor vessels, they get it immediately, pulled from other construction projects. Nothing has higher priority than synthetic rubber. Summer 1942. The first experimental batches of American-made Buness emerge from pilot plants. The rubber looks right. It has the correct texture, the right elasticity. But testing reveals problems immediately. Tires, made from the early Buness formulas, last only 5,000 miles, compared to 25,000 miles for natural rubber tires. The rubber is too soft. It generates excessive heat during operation, causing premature failure. The Army tests the experimental tires on Jeeps at Aberdeen Proving Ground in Maryland. The tires fail catastrophically. Some disintegrate after just 2,000 miles. The military rejects the early Buness as unsuitable for combat operations. Bradley Dewey, president of the Rubber Reserve Company, convenes an emergency conference in August 1942. Every major rubber company sends their top chemists to Washington. The question is simple. Can synthetic rubber be fixed, or should America pursue other options? The chemists argue for days. Some want to abandon Buness entirely and focus on other formulas. Others believe the problems can be solved with refinements. The disagreement threatens the entire program. Dr. Harry L. Fisher, from U.S. Rubber Company, proposes a solution. The problem isn't the chemistry, it's the ratio. German Buness uses 75% butadiene and 25% styrene. Fisher's team experiments with different ratios and discovers something remarkable. Changing the mix to 77% butadiene and 23% styrene produces dramatically better results. It seems like a trivial change, just 2 percentage points. But those 2 points alter the molecular structure of the polymer chains. The new formula creates rubber with significantly improved heat resistance and durability. The modified formula goes into immediate testing. In October 1942, tires made from the new Buness formulation run for 15,000 miles before failure. It's still not as good as natural rubber, but it's close enough for military use. The Rubber Reserve Company approves the formula. Every plant under construction will use the Fisher ratio, 77 to 23. The first full-scale synthetic rubber plant comes online in April 1943. The Goodyear facility in Akron begins continuous production, running 24 hours per day. The plant produces 80 tons of rubber on its first day of operation. Within weeks, problems emerge. The polymerization reactors clog with residue. The rubber coming out is contaminated with impurities. Quality control engineers discover that small variations in temperature, just 3 or 4 degrees, create completely different products. The solution requires precise instrumentation. Engineers install hundreds of temperature sensors throughout each reactor. Automatic control systems adjust heating and cooling continuously, maintaining exact conditions. It's some of the most sophisticated industrial automation of the era, comparable to aircraft engine manufacturing. By June 1943, 8 synthetic rubber plants operate across the United States. Total production reaches 20,000 tons per month. It's progress, but still far short of the target. The military needs 70,000 tons per month by year's end. The bottleneck shifts to raw materials. Butadiene production can't keep pace with demand. The petroleum refineries run at maximum capacity, but there's not enough. The War Production Board orders construction of additional butadiene plants, but they won't be ready until early 1944. Chemical engineers find a temporary solution: produce butadiene from grain alcohol instead of petroleum. The process is less efficient, but uses existing resources. Distilleries across the Midwest convert from beverage alcohol to industrial alcohol production. Millions of gallons of ethanol, normally destined for whiskey, get diverted to rubber plants. The grain alcohol process produces lower yields, requiring 4 gallons of ethanol to make 1 pound of butadiene compared to 2 gallons of petroleum. But it works, and it keeps the plants running while petroleum capacity expands. Operating a synthetic rubber plant requires specialized skills. Each facility employs 1,500 workers across 3 shifts. Chemical engineers, reactor operators, laboratory technicians, and maintenance crews. The work is dangerous. The chemicals are volatile. Butadiene is highly flammable. Styrene produces toxic fumes. One mistake can kill. The industry faces immediate labor shortages. Most experienced chemical workers are men, and most men of working age are being drafted into military service. The solution: recruit women. By mid-1943, 40% of synthetic rubber plant workers are women, many with no previous industrial experience. The companies create accelerated training programs. New workers spend 2 weeks learning chemistry basics, safety procedures, and equipment operation before starting on the production floor. Experienced operators mentor the new hires, teaching them to read the instruments, adjust the controls, and recognize when something goes wrong. The safety record is remarkably good, considering the pace of expansion. The synthetic rubber industry experiences fewer accidents per worker hour than traditional manufacturing. The reason: everyone knows the stakes. The signs posted throughout the plants read, "Every pound of rubber you make saves American lives." Natural rubber remains the standard. Synthetic rubber needs to match it, or come close for each specific application. Military engineers test every batch. Tires are the most critical application. By late 1943, Boone tires last 18,000 miles, compared to 28,000 for natural rubber. The Army accepts them, but tire companies continue refining the formula. They experiment with different vulcanization processes, add carbon black for reinforcement, and adjust the curing time and temperature. Gaskets and seals present a different challenge. Boone swells in contact with oil and gasoline, causing leaks. For these applications, DuPont's neoprene works better. By 1944, nearly all military gaskets use neoprene, while tires use Boone. The strategic reserve of natural rubber gets allocated to aircraft tires, where the demands of high-speed landing and takeoff exceed what synthetic rubber can handle reliably. Each rubber plant has an on-site laboratory, testing every batch. Technicians measure tensile strength, elongation, heat resistance, and cold flexibility. Only batches meeting military specifications get approved for use. Rejected batches go back into the process for The Army's Quartermaster Corps publishes detailed specifications for every rubber product. A Jeep tire must withstand loads up to 1,200 pounds. Operate in temperatures from -42 plus 120 degrees Fahrenheit, and resist punctures from shrapnel and debris. Meeting these requirements with synthetic rubber takes constant refinement. December 1943. America's synthetic rubber industry reaches its target: 700,000 tons per year production capacity. The achievement is staggering. 22 months from crisis to solution. 51 plants built from scratch. An entirely new industry created under wartime pressure. The statistics tell the story. Total production in 1943, 231,000 tons of synthetic rubber. Total plants operational, 28, with 23 more under construction. Workers employed, 42,000 across all facilities. Raw materials consumed, 2 billion pounds of butadiene and styrene. Investment, $700 million in construction costs. By January 1944, synthetic rubber production exceeds natural rubber imports for the first time. America produces 55,000 tons of synthetic rubber that month. Natural rubber imports, coming now through limited channels from South America and Ceylon, total 38,000 tons. The military begins converting entirely to synthetic rubber for all but the most critical applications. Jeeps roll off assembly lines with Boone tires. Trucks, tanks, and half-tracks use synthetic rubber gaskets and seals. Supply officers stop worrying about rubber shortages and start planning for surplus. The transformation is total. In January 1942, America's synthetic rubber production was zero. By mid-1944, the nation produces more synthetic rubber than the rest of the world combined, including Germany, which pioneered the technology. The ultimate proof comes from field testing in combat conditions. In June 1944, the Allies land at Normandy. The invasion force includes 50,000 vehicles, most equipped with synthetic rubber tires. Military observers track tire performance under actual combat conditions, driving through mud, over rubble, across beaches, through forests. The reports from France arrive in August. Synthetic rubber tires perform acceptably. They wear faster than natural rubber, typically 12,000 miles versus 22,000, but they're reliable. More importantly, there are enough of them. Supply lines deliver replacement tires to units in France within days of requisition. In the Pacific, where temperatures and humidity test materials to the extreme, synthetic rubber faces harder challenges. Jeeps operating in New Guinea report tire failures at 8,000 miles. The heat and moisture degrade the synthetic compounds faster than in European conditions. Chemical engineers respond with a tropical formula, adjusting the vulcanization process and adding different stabilizers. By late 1944, Pacific Theater tires last 11,000 miles, approaching acceptable levels. Intelligence officers captured German synthetic rubber facilities in 1945 and conduct detailed assessments. The comparison is revealing. Germany produced 120,000 tons of synthetic rubber in 1944. About 20% of American output. German Buna rubber is comparable in quality to American Bunas, but German production suffers from material shortages and Allied bombing. The critical difference: scale. America built 51 plants, Germany built 7. American production capacity is 7 times larger, and American plants are safer from bombing raids, allowing continuous 24-hour operation. German engineers tell interrogators they knew about the improved 77-23 ratio, but couldn't implement it. Their plants were designed around the original formula, and retooling during wartime was impossible. They continued producing inferior rubber, because changing the process would have halted production for months. The documents reveal something else. Germany's rubber shortage was worse than America's. By 1944, German forces were stripping rubber from civilian vehicles to keep military equipment operational. The German army's mobility declined, partly because trucks and vehicles couldn't get replacement tires. The question becomes, how many American lives did synthetic rubber save? The calculation is complex, but military historians attempt it. Without synthetic rubber, the American military would have faced severe mobility constraints. By late 1943, the strategic reserve would have been exhausted. Tire rationing would have grounded vehicles. Operations would have slowed or stopped entirely. Some estimate the war in Europe would have lasted an additional year without adequate rubber supplies. Japan's war might have extended even longer. Each month of extended war meant thousands of additional casualties. Major General Brihan Somerville, commander of Army Service Forces, states in his 1945 report, the synthetic rubber program was as critical to victory as any single factor, except manpower and ammunition. Without it, we could not have maintained mobile operations on 2 fronts. The D-Day invasion required 600 million pounds of rubber in vehicles and equipment. Only half of that could have come from natural rubber sources. Without synthetic rubber, the invasion either doesn't happen on June 6, 1944, or it happens with insufficient vehicle support. May 1945, Germany surrenders. The war in Europe ends, but synthetic rubber production continues at full capacity. The Pacific War still requires massive supplies, and the plants run 3 shifts daily. August 1945, Japan surrenders. The war ends. The government faces a decision. What to do with 51 synthetic rubber plants representing $700 million of investment? Some suggest closing them and returning to natural rubber imports. Now that Southeast Asian plantations are accessible again, the tire companies argue otherwise. Synthetic rubber production costs have dropped from 55 cents per pound in 1943 to 18 cents per pound by 1945. At that price, synthetic rubber competes with natural rubber economically. More importantly, synthetic rubber's properties can be customized for specific applications in ways natural rubber cannot. The government sells the plants to private companies at fraction of construction cost. Goodyear, Firestone, US Rubber, and Goodrich buy the facilities and continue production. The industry transitions from military to civilian markets. By 1950, America produces over 1 million tons of synthetic rubber per year, and 70% of it goes to civilian products: automobile tires, industrial belts, footwear, and consumer goods. The wartime crash program created a permanent industry. The synthetic rubber program demonstrated American industrial capacity under crisis conditions. The achievement required coordination between government, private industry, and science on an unprecedented scale. The lessons shaped post-war industrial policy. When future crises emerged, policymakers remembered how quickly America built the synthetic rubber industry. The model of government-industry partnership, rapid scaling, and shared technology became a template. The chemists who developed synthetic rubber went on to create the plastics industry. The polymerization techniques perfected for rubber production applied directly to plastics manufacturing. By the 1960s, synthetic polymers had transformed American life, and it all traced back to the wartime rubber crisis. The engineers who built the plants applied their experience to other large-scale chemical facilities. Post-war petroleum refining, petrochemicals, and pharmaceutical manufacturing all benefited from the knowledge gained building synthetic rubber plants under pressure. Bradley Dewey, president of the Rubber Reserve Company, coordinated the entire program. He navigated political pressure, industry disputes, and technical challenges while keeping 51 plants on schedule. His ability to force cooperation between competing companies was essential to success. Dr. Harry L. Fisher, the U.S. Rubber Company chemist, who discovered the improved 77-23 ratio, received little public recognition. His adjustment of 2 percentage points changed everything, but his name appears in few historical accounts. He continued working in polymer chemistry until his retirement in 1962. Jesse Jones, Secretary of Commerce, provided the political support and funding. He convinced Congress to appropriate $700 million for an unproven technology during a time of competing priorities. Without his backing, the program would have failed. Waldo Semin at B.F. Goodrich contributed to multiple improvements in the polymerization process. His work on catalysts and reaction conditions helped standardize production across all plants. He held over 100 patents in polymer chemistry by the end of his career. The 42,000 workers, many of them women with no previous chemical industry experience, operated the plants and produced the rubber. They worked dangerous jobs under pressure, knowing that every batch mattered to the war effort. Between January 1942 and August 1945, America produced 2,500,000 tons of synthetic rubber. That rubber equipped 12 million military vehicles. It supplied the tires for 50,000 aircraft. It provided the gaskets and seals for every ship in the Navy. Without it, America's mobile warfare strategy would have been impossible. The program succeeded because of speed, scale, and cooperation. 51 plants built in less than 3 years, an investment of $700 million, paying off in mobility and victory. Scientists sharing research across competing companies, government and industry working toward a single goal. The crisis that seemed impossible to solve in December 1941 was resolved by December 1943. America turned petroleum into rubber, desperation into innovation, and impossibility into industrial triumph. 12 million vehicles kept running because chemical engineers refused to accept that synthetic rubber couldn't work. They made it work.